Professor Yoshihiko Nakamura is the head of the Department of Mechanoinformatics at the School of Information Science and Technology at the University of Tokyo, Japan. He received a PhD from Kyoto University. After working at Kyoto University and the University of California, Santa Barbara, he joined the University of Tokyo in 1991. His current fields of research include humanoid robotics, cognitive robotics, neuromusculoskeletal human modeling, biomedical systems, and their computational algorithms. He is in the top 100 of the most cited researchers in robotics. He served as president of IFTOMM from 2012-2015. He's a foreign member of Academy of Engineering Science of Serbia, distinguished affiliated professor of Technical University of Munich, Germany, executive member of International Foundation of Robotics Research, fellow of several organizations, including Robotics Society of Japan, IEEE, and World Academy of Art and Science. The title of his plenary talk today is Mocap as a Service. Video motion capture makes human motion analysis for everyone.
Thank you, Professor Fernando Bolio, and thank you for the other organizers. I'm really honored and happy to be here to talk about our recent works. But my title today is about this. It's already explained, and it's based on many of our students and collaborators and other people who supported this work. Well, in our lab, we have been working on robotics for many years, and our focus for these maybe 20 years is on the humanoid robotics. So humanoid robotics, we have in this category, we have published several papers, and this is one of the new one published in 2 weeks ago in Beijing in humanoids. And we developed all kinds of the actuators, hydraulic actuators, and try to develop very force-sensitive, lightweight actuation system for complex robot like humanoid. And we could show very force-sensitive control, result of the control, and succeeded in some preliminary working experiment. Well, for us, the machine intelligence is basically humanoid robotics. So mechanism control, this is what I have already shown. But in addition to that, we have to learn from human motions, from human data. So taking the data, we have to segment and categorize and connect with languages for communications. And in addition, we discuss the human sensations to establish the better human-robot communications. Of course, not only those software development, we have to develop the efficient algorithms for real-time applications. So we have worked on these for, as I said, 20 years or so. And, well, I hope it... So, in addition to humanoid robot, we have more and more involved in human side. And basic technology we use is the well-known motion capture technology. This is quite commonly used in many applications. And the left-hand side is the one with the reflective markers. What you see, white dots are the reflective markers. It's a ball with reflective screen close. And by projecting the infrared light from the camera, each camera can see the markers very clearly. And taking account of all the cameras, the system can detect the coordinate of each markers. Then we have to work on the 3D reconstruction of the body movement. On the right-hand side, more recently, the IMU, gyro or accelerometer, are being used for the motion capturing. It is simpler because there is no huge environmental setup, but still a subject have to wear some equipment on the body. Well, this is the setup in our lab. We use the marker motion capture system, maybe 10 or 16 of them at a time. And in addition, we have the wireless electromyography. We attach typically 16 of them. Sorry. We attach typically 16 of them to the body. And in addition, we use the fluor contact force sensors. And we take all the data and then analyze the human motions. So this is what the motion capture system, camera system can provide. Right-hand side is a signal of EMG detectors. And then by applying the inverse kinematics in robotics, we can reconstruct the movement of the skeletons. We developed these skeletal systems. And maybe around 15 years ago, some of our students worked hard and put all the muscle system on the body. And the muscles are modeled by massless wires. And the wires are pulling the bones. So we attach all the mass properties to the bones. So bones are very heavy. Bones weigh the total of the human body. So currently we have 989 muscle wires and many other wires for the constraint. Well, this is one typical result from the analysis of bones. By measuring the bone movement, we segment the movement, unsupervised automatic segmentation, and then make the classifications and symbolizations. And afterwards, we attach some verbal symbols to the movement statistically. And then this is the based on the data set that my collaborator, Professor Wataru Takano, took from his daily life. He wears the IMU motion capture system and collected 260 hours of data. And then using the crowdsourcing, he got the annotation of the movement by people, and then build this system. So what it can do is that by looking at the movement, then the system will infer some words and then put into the sentence. The 3 sentences here are in the order of the probability inferred from the movement. And this is the case when the Professor Takano is doing his lecture in the classroom. Of course, this system is based on only the movement data. It doesn't use the face identification or any object recognitions. And we are working on adding those additional information to make sentences more realistic. Well, the same technology can be applied in many fields. We had collaborated with the Fujitsu laboratories, and they announced, I think, last week widely about the automatic scoring system of artistic gymnastics. They demonstrated 2 weeks ago in the World Championship. And our system can segment the movement and compare with the non-movement and being used for the basis of the de-scoring system. Well, for the analysis of muscles, we applied the robotics technology very straightforwardly. So we basically reconstruct the bone movement. Then we can identify the joint angles, joint velocity, joint accelerations. Since we attach all the mass properties to the bones, we can compute the forces and torques interacting between the bones and the environment. And then we solve the wire tensions. And the relationship between joint torque and wire tension is linear and quite simple. But problem is that what we can measure is at most around 200 variables. But what we have to solve is over 1,000, sometimes nearly 2,000. So information is very little. So we have to use the optimization and some criteria to solve the data. So we first solve this kind of quadratic programming and compute a contact force. And then we use that contact force result to solve the wire tension. So we use the quadratic programming twice. Of course, we use a very famous but simple model of the mass activities. Mass activity A is linear to the mass tension. And the coefficient is coefficient consisting of three components. One is a constant F max, that is the maximum force of each muscle. And FL and FB is a scalar function. And FL is a function related to the length of the muscle. And FB is a function related to the velocity of the muscle. So we have to compute these functions. But the muscle force is linear to the mass activity A. So we sometimes asked by the broadcasting station to help their program. And in 2012, we had a chance to measure this female, the silver medalist of the London Olympic. She came to our lab a couple months before the London Olympic. After the measurement, we can compute the muscle activities and visualize in this way. So as technicians or engineers, we can show how she used the muscle activities from our computation. And some top athletes like her use the one side of muscles and try to avoid co-contractions because that is more efficient and that can make a faster and larger force. And this result is clearly showing that kind of result. We can tell a little more than that, but let me show some other interesting example. In 2014, the same TV program tried to measure the football players like the Andres Iniesta and Sergio Gomez. And after 3 times of cancellations, we succeeded to capture his data for only 1 hour in Barcelona. And 2 of our students and the staff of the broadcasting station came to Barcelona. And I have a good friend of Technical University of Catalonia, Professor Carmen Torres asked her colleagues to let us use the motion capture studio of the university. And we invited them to come and spend 1 hour to take this. Well, in 2016, this was a very hard case. Judo players, and the right-hand side person is the Mr. Ryunosuke Haga. She got the bronze medalist in the Rio Olympic. And we have to have the judo wear. Without judo wear, they cannot play judo. So anyway, the difficulty was how to identify the contact force between the 2 players. So one of our PhD students have to develop new heuristic idea to solve the contact force without sensors between them. And what was surprising is that this is the rectus femoris of the right leg and left leg. Upper one is the rectus femoris of the Mr. Haga. And when he throws the opponent, the right-hand side rectus femoris activated within 10 milliseconds This doesn't include the neural activities. This is just show the activity of the muscles, but it's very first activation of the muscles. In 2017, we brought whole of our system to Osaka and measured the Asian female champion. She was 70 years old at that time. So this is how we prepare. We attach EMG detectors, and she has a ball and some square stuff, right? Balls are the reflective markers, and square stuff is the electromyograph wireless transmitters. And we attach all of them and measure the performance. She is very famous for very special, a kind of smash, but it's not smash. It is called Mima punch. It's very famous finishing stroke for her. And we investigated how she uses all the muscle activities. And we asked her and her opponent to play rally 3 times and smash afterwards. So the orange is the side view of the movement of the racket of herself, and the blue one is the movement of the racket of the opponent. And the Miss Ito is a rather small lady, and she plays very near the table. So the stroke is very precise and small. And we attach the microphone to very precisely detect the point of ball contact on the table. And this is the upper graph is the upper body muscle activities of the Miss Ito. And you can see black line after 3.5 seconds. That is the time when Mima Ito made the smash. And you can see which muscles she used for that kind of smash. This is very interesting investigation, and I can tell a little more, but let me skip. So the difficulty, I mean, we can use our technology for measuring the top athlete and some special cases, but we cannot measure everyone. We cannot measure many people because for the preparation, it takes at least 1 hour. Just to attach nearly 40 markers and 16 EMG detectors, to do everything, it takes at least 1 hour. So it's a quite heavy work for us. And if the motion capture technology becomes the commodity so that everyone can use, I think the software part is quite easily implemented. So if it can be done, not only the top athlete, we can use a system for the education of young athletes or juniors or many people. And sports hobbyists or fitness club members. I'm a member of a fitness club, but I'm happy to use it if the club has one. And of course, by measuring the movement of the elderly, just by measuring the movement of skeleton, one can tell that the feet of the elderly person is going down, or shoulder movement range is going too small. That kind of measurement can be done quite easily only by motion capturing system. Well, in order to make a Mocap a commodity, we have to cost down the time, space, and expense, and of course, human hand. There are a lot of human hand and human works after measurement to visualize. So we worked on this. So this year, some of our students worked hard and developed the video-based motion capturing. And this is what one of our ex-students, Mr. Ohashi, presented in Madrid a few weeks ago. So as you may be aware, it is very famous software, OpenPose, that was developed by professors in Carnegie Mellon, and it can detect from 2D image the position of the joint. And if there are many people, it can detect which joint is which person's, right? So this is very smart system based on the deep learning. So we decided to use that system for the case with multiple cameras and try to develop the smooth 3D reconstruction of the movement. Well, this is our setup. We use the 1K camera at 60 Hertz. And of course, some of our students, actually 3 master students worked on the problem. And for 3D reconstruction, we have to smooth in space and time the whole measurement from 4 cameras. So it was quite hard work. And this is a result for regular motions. By saying regular, this is irregular motions. So if the position of arms and legs are upside down or opposite, or person is laying down, since the open pose is basically trained based on the walking or running or dancing, so for regular motions, it works perfect. But for irregular motions, there are many problems. So we have to work on this, and it is still a problem. But one small idea is just to rotate the image so that person's figure always appears as regular way. This is very simple idea, but it works. So if we rotate, the result is the right-hand side. Well, it sometimes fails, but it still works. Maybe. So we went outside to the ground and we measured the training of the soccer team. The 4 people are doing some training. And the long stick is showing the direction of the nose. That means that is showing the intention, or that is showing the attention of the persons. So by applying this for the whole team, we can investigate the detailed performance of each player, as well as the collaboration and the communication between the players in the ground. Well, this July, we had a chance to measure the futsal game. So 2 famous Italian players came to Japan, and with other famous Japanese players, they played futsal in the very hot day in July. And we brought 12 cameras and tried to capture the movement in the half of the court of futsal. That means 20 meter by 20 meter. So these 4 cameras are capturing the excellent play of famous Italian player. He received a direct pass from the goalkeeper and made a direct shoot. It was a very beautiful scene, but the image was like that. And from the image, some of the students worked hard and reconstructed the movement of the bone and reconstructed the muscle activities. Of course, our goal for these cases is to measure all players on the ground, which is still ongoing project in our lab. Well, we have reduced the time, space, and the cost. We only need, at this case, we need cameras, maybe at minimum 4 cameras. But still, we have to work afterwards to reconstruct and analyze. So afterwards, in this May, we just developed this system. With 4 cameras, this is my office, and no other systems, no force plate. And the 4 rather big desktop computers are computing the open pose and other reconstruction tasks in real time and showing the muscle activities. The latency is 0.5 seconds. And the camera frame rate is 30 frames per sec. This is the maximum frame rate we can do in real time. So for this case, no human hand, right? So the 30 frames per second is not really good, but it's quite easy. We can change from person to person. This is a guy working on humanoid robot. Well, even difficult clothes like hers, we can somehow reconstruct the movement. This is my ex-student learning ballet, and this is myself. Okay. So it's not hard. So video motion capturing system, Mocap, it can develop, it can be applied for many applications. So with only cameras, we are ready to make a software as a service. I could say Mocap as a service. Only getting the image data from the cameras, sending the data to the network system, everything can be done without human interventions and feedback the result. This is what we want to see. So in Japan, there's the academic network that is called SciNet 5. And SciNet has 100 gigabyte network and being released for academic use. So using this, we can send image data from almost everywhere to Japan through this network to our university, or maybe other cloud service providers. And then we'll be probably computing the result. Currently, in our School of Information Science Technology, we have a rather small cloud experimental system, and we are implementing the video mocap prototype in this system so that we can do the mocap as a service. And this is one good example. This paper is a very famous paper investigating the biomechanical measures of neuromuscular control and valgus loading of the knee and predict anterior cruciate ligament injury risk in the female athlete. It's a long title, but by measuring the jumping motions and collecting the data, it may be possible to compute the risk of the knee injury. And basically they measure the knee angle, whether knee is going inside or outside and what is the angle. That is the main measurement. And the targeting injury point is this ligament. So this ligament is typical portion of the injury. And sorry for the Japanese slide, but collaborating with the medical doctors in our school, he is the team doctor of one of the professional soccer team in Japan, and he is helping the many sports club in our universities. And he brought 282 students in 3 days to our lab and measured this kind of movement. So they were in a line in the corridor, and they come to our lab one after another for 3 days. So we measured with 60 frames per second, and we can reconstruct this kind of movement. Well, of course, we can solve the muscle activities, but basically in this case, the target is measuring the skeletal movement and provide the knee movement. Well, with the video motion capture system plus high-speed network plus cloud computing, we can build a mocap as a service. And with this, I think the motion capture technology can be used for everyone at quite a reasonable cost. And for the society, this is a chance for the business to healthcare and sports, and probably for other businesses, maybe sports, game entertainment, or customer monitoring for retail store. This is quite different, but it's maybe applied. Well, in conclusion, based on humanoid robotics technology, we have been involved in the measurement analysis and the making big data from the human movement. I think it is almost ready to take a lot of data of humans and make the consensus or make the advice about the movement of humans. And the application field can be rather big, but we are interested in sports, health service, network communication providers, and technology developers. Okay. Thank you very much.
For these great presentations. Now we have some time for questions.
Okay.
Thank you for a great talk. So when you were presenting Mocap as a service, you mentioned the cost of the system. So how would you replicate, how could a normal user, just a common man, replicate the approach using cameras? So are there cameras you could go to a supermarket or technology store and just buy them? And how good do they have to be?
Okay, so in the current system, we use the industry standard cameras, typically 2K cameras and 60 frames per sec. And more importantly for us, we want to synchronize all of them. So synchronization is our requirement currently. So the one camera costs a few $100. In addition, we use a few $100 of lens. That all of them. So other part is all the cost of the computing. So, but synchronization may be not necessary in the future. We can accommodate if we know some the timestamps of the image, and probably we can use the rather inexpensive cameras. We have to carefully make identification of each of them, but still probably we can use. So the camera system can be reduced by cost, I think.
Thank you.
Yeah, very nice talk. So you start with a humanoid robot and you're studying muscle behavior, et cetera. And then you go to humans and map it over there, study humans. Do you feed that back into your robotic system after learning how humans do things optimally? Can you map that back to your humanoid robotic to make it better?
Well, that is common question or criticism. When we submit our paper on these technology in robotics conference, the reviewers always criticize what is the relationship with robot. But I could say this is heavily based on robotics technology. And we can use some of them for humanoid robot. And other technology can be straightforwardly applied for more healthcare or other field of science or technology. For the humanoid robot, it is really important to develop natural actions. That means that the humanoid robot should behave naturally when people see the robot movement or interact with the robot. So that must be based on the data set of human movement. In addition, of course, humanoid robot have to understand the human movement and try to develop necessary service to the persons. So the capturing human data and storing them and extracting the knowledge from them is essential part of the humanoid robot. For those purposes, certainly it's being used. And what I don't know, but I'm expecting is that still the humanoid robot control is a difficult problem. The biped work or any legged locomotion is very difficult control problem. So there are some works on how to use the biological the knowledge to develop the better or more stable motion for the robot. Maybe neuroscientific technology can be used for that, and or maybe whole body maneuvers, including muscle and neurons, may provide some hint for building the more reflective motion of the humanoid robot. That is a very future-looking kind of discussion, but that is also the direction of interest.
Okay, thank you.
Thank you.
Another question here?
Yes.
Really thank you for this great talk, but I have a question. Did you made in your application before any measurement or link between the heavy load or the load in the muscles and also burning fat? Maybe it will help people who would like losing weight.
Burning
yeah.
fat. Good question, actually. Actually, with one of a visiting professor from Beijing, we have been working on building the mathematical model of the energy system of human body. So we are, from this kind of analysis, we can rather precisely or maybe computationally estimate muscle activities. And we can track the temporal curve of the whole movement. And we are talking about how to compute the use of ATP or other energy source and how to reproduce from the fat or lactose. So those biochemical system can be connected with this musculoskeletal system of the whole body. That is actually one of our current interests.
Thank you, Professor Nakamura. I enjoyed your talk.
Thank you.
For the Mocap system, it's a kind of takes a lot of time and effort to attach, the markers with reflective materials. But these days, there are depth sensor-based cameras. The speed is increasing, getting much better, and all that. And is there any possibility that we can remove, those, the tedious work of attaching?
Sorry, remove what?
Remove tedious work, the effort of attaching those markers on the human body.
That's right. So, well, I believe the video system is very strong system. The resolution is getting higher and higher, and capturing speed is getting higher and higher. So information-wise, the image or video system is very, very promising. And with the marker system, there are a lot of tedious works for preparation and after measurement. So I think we can remove most of them. Of course, we have to do the camera calibration, camera setup, network setup. That is another headache for us. And as you might said, the RGBD system, that is another good sensing system. But still, the depth camera system, by the resolution point of view, I think camera system is much more promising. And actually, the Fujitsu for the automatic gymnastic scoring system, they use their own laser scanning system. That is useful. But as resolution-wide, I still believe that camera system, if it is possible, it is more convenient.
Thank you.
Thank you.
Okay, thank you very much. I'm sorry there is no more time for questions, but you can maybe ask him in the coffee break. Let's thank the speaker again.